My name's Nicholas. I am a associate lecturer at Macquarie Uni in the engineering department. Today I'll be talking to you guys about what 3D printing is doing to the society currently and where it's going to go ahead. What are the positive impact as well as some of the consequences of 3D printing and in general additive manufacturing. So I assume that a lot of you guys have 3D printers at school as well. I know last year when I visited the LEAP program, I saw a few systems being set up and it's being rolled out to a lot of schools. So no doubt you guys probably had your play with it a bit as well. But 3D printing falls under this whole topic of additive manufacturing. So the definition of additive manufacturing is a layered by layered construction of materials, and it does not restrict to what the type of materials that you're using. In the definition, according to the American standards, it simply says joining of materials. So that really opens up to different types of materials being used. In the past, it's conventional to use plastic, but as time goes on, we're seeing more and more metals as well as alloy type of materials. So how does this differ from subtractive manufacturing? Now, traditionally, you would design your piece of, say, parts using drawings of some sort. So, computer-aided drawing, modeling, and optimization. After the design, often they'll go through a phase of prototyping. So that's often a one-off process, and this is really costly for a lot of firms. So in the past, there's not been a lot of engineering firms that has that capability, and rapid prototyping is actually a very important part of this engineering process. After that, you will have full-scale manufacturing capability. So again, at that point, you have a lot more investment into processes and equipment. What additive manufacturing does, though, is that it streamlines this whole workflow from design process all the way to manufacturing production. And in some cases, as we'll later see, it actually would change a lot of the how things are planned out and the investment made by companies. So when did all this kind of started? Well, it started in 83, around the 80s, with Chuck Holt designing this first idea of printing an object or creating an object from a scan, all right, from a light scan. And he called it Stereolithography, which is a bit of a mouthful, but this is the standard file type that you're using for all 3D printers now, STL files. So you can see from this map here, I went onto Google and just searched up the term, and there's been a dramatic increase in the reference of this word in the last 30 years or so. Now, back then, the first system was sold for about 200K. Now, obviously, right now, the price has dropped a lot, so you can see how technology kind of came through. So that was the first conceptual idea and actually the first practical print that they've made. Since then, there's been a range of systems. Now, what can you do with this type of systems to generalize it to a lot more other material types? So the two principles in designing an additive manufacturing system is the ability to control material deposition, which is how materials are being extruded or layered, and also how to bind those materials together. So, in the definition, it says layered by layer, which if you think about it, it's in all sense. So you can either extrude your materials, that could be plastic or polymers in general, metals, metal wires, you can then fuse them, or maybe even ceramics. Once this is layered, you can then go to the second step of fusing them. So apart from the layer by layer deposition method, you've also got the powdered method of the depositing materials and liquid polymers. We'll go through at it later in the next few slides as to what those different system really means and how some of the system works better with the different materials types. Control of the fusion of the materials, it's very important because that defines a range of factors such as density of the material, the mechanical properties, as well as the surface finishing. So I'm sure that you've seen those desktop 3D printers. You can actually see the different layers in them. But some of the more professionally done or more production grade type of prints, you actually cannot see those lines. And that comes down to resolution. With the use of different polymers, you can also make use of chemical reactions. So hard plastics such as whatever plastic that you see around you, as well as some of the elastomers, rubbers types, they can be intermixed and create a range of materials with different properties. For the use of metals and ceramics, often you also want to have an inner atmosphere, which is basically an atmosphere without oxygen or controlled oxygen. That allows you to create systems or material parts that does not have oxides in it, which in some cases is detrimental to the property that you're using the parts for. So just a quick search online, you can see these are the range of 3D printers, desktop 3D printers, and price ranges from low 200s all the way to mid thousands. So 6,000 is a pretty expensive system. These are all plastic extruded systems, so we're not even talking about metal printing. We're simply talking about plastic printings. Now you might wonder, well, why exactly is this the case? Why would the price vary so much? Well, it turns out that the price is often correlated to the print size, so how big your print can be, as well as the resolution, which comes from the different ways of generating those prints. So without knowing too much about this, not all 3D printers are the same. Depending on your application, you can go all the way to satellite type of equipments, down to your normal models that you play around or you use at home for demonstration. So the different types of 3D printers out there can be classified based on this chart. Namely, you can classify them with the type of material that they interact with, and or the way the materials are sintered together. So I'm just going to go through in the different sections here what the different types and what their differences are. So this is the first system that was created in the 80s, right? With the use of a laser beam, being able to polymerize the plastics or the polymers in general throughout this liquid container of resins. So this was used as a method to rapid prototype designs. Often a company comes with a design, they want to quickly just scale it up, or not scale it up, quickly demonstrate how the part works or how it all fits together. They will employ an external company that has such a system and they will get a print done. This is often costly, but because of the way it's using lasers and the resolution of light, it can have a high resolution. It's mainly used for polymeric materials, so plastic, it's a common one. And can be used for a range of rapid prototyping projects. So what it does is you have liquid photopolymers, which is polymers reacting to light, saturated, and you will have your laser head coming down to just basically etch out the different layers. And as the different layers is being etched out, the bed drops. And so the next layer can be drawn. So through this process, you can sinter the parts layer by layer. Now, since then, they realized, well, if we can do with polymers, photoreactive polymers, why can't we do it for metals? And that's exactly what they did next. They used powdered or metal powders, so fine grains of, say, titanium, a range of space alloys, and they use the same laser, probably high power, to basically melt them or sinter them. Now, there's a slight difference between sintering and melting. So melting is a complete melting. It's almost like chocolate just melted into a puddle of melted chocolate. Or you can have soft chocolate, right, which is the sintering. And that allows you to create geometries that has a lot of porosity. So if you don't fully melt each of those metal particles, you can actually create systems that has a lot of pores, and it could be useful for, say, bone implants, where you actually do want that type of porosity to facilitate cell growth. But in both cases, it's exactly the same. You have a supply of metal powders, which then is pushed into the chamber where your actual print is, and the laser simply just scans or raster the different layers. And as you get the first layer done, the bed would drop down, and then subsequently the print will be developed. GE has actually used this method to manufacture some of the next generation turbines or engine. So that it's actually being used to full production now. So it's of production grade. It can be suiting for polymeric materials, metals, and ceramics. Generally high resolution, but very costly in terms of investment into the printer. And if you're working with ceramics, you're often required to do a secondary process, which is when you kind of sinter the material or have the shape formed, you put it into an oven to fully densify this part. This field deposition modeling is what you all have been probably seeing everywhere. There has been an explosion of this type of technology in the late years. So it's what you typically see. It's this extrusion of plastic onto a print, and it builds it up. It doesn't actually. The system actually constructs exactly what the part looks like. With the development of a range of material types for the spool, you can get things like soft polymers, you can get different colors polymers, you can even get things like carbon fiber prints. So if you want to print a carbon fiber part, you can actually have carbon fiber spools purchased and used in the print. So it's used for, again, a range of rapid prototyping projects. It's very diverse. Can't really be used with ceramics. However, there is development that you will put, say, gold powder or silver powder in with the spool, and once you print it, you would then bake it. And that baking process removes the template, and so you're left with this the silver material. And often, backyard kind of jewelers, they actually use this way to generate some of their jewelries, which is, I think is pretty cool, because now it just simply means anyone can have that capability or manufacturing capability that traditionally has been tied to big companies. And it's often low cost or to kind of high cost of $6,000 a piece of equipment. Okay, so the next two type of printers are what you normally, again, won't see commonly. It's used in, say, medical industry because of the setup. So similar to the selective melting, this system uses electron beams. Now, why would you opt for electron beam? So one reason is because you get really high focusing, as well as a very quick melting time. So, compared to laser where you heat it up and it forms a bit of a plasma around your nanoparticles or metal particles, you've got this negative effect of heat. Whereas in an E-beam, heat is not too much of an issue. It's also very useful to generate things like or prints without oxygen. So often bone implants such as this, it's made from E-beam, the lithography, and that's because you don't want oxides in your print. Oxides in metals actually weakens the metal, so you want a really dense material that can be used in the bone rather than oxides or rusting in general. So, oxide is just another or technical term for rusting. It can create really porous materials types or parts with a rough finish for cell proliferation. And the method is very similar. You have the metal powder coming in, and then your bed dropping down below. Okay, so the last school of printers is this laminated object manufacturing, or what one of the company calls it is projection-based lithography. So this is rather interesting, and I suggest when you have time, you go on YouTube and just look for this company and see some of their demo. I'm not sure about the copyright issues, so I didn't include the whole video in here, but what they basically do is has a pool of resin, and the print basically pulls out from the resin. And they're able to do that because they can project the image or the cross-section in the glass window underneath the pool of resin. So this company has published a science paper which in the field of research is actually pretty significant. And they claim that with the control of light projection, which is what you generally do with the rastering, as well as the chemical properties or reaction, they can actually create systems like that and print really fast, or print the job really fast. So you can see they're able to pull this object from this pool of resin, which is this yay thick. It's pretty incredible. The system, however, costs $40,000 a year just to rent. So they're not selling you the system because of patent issues or intellectual property, but they're renting you the system. And they claim that they could revolutionize some of the industry because some parts that could be generally can be made can be markedly reduced in cost with this system used as a production type. So at the moment, it's only for polymeric materials, but even having said that, the range of properties you can get from polymers, it's incredible. You have things like really hard plastic all the way to soft ones. Nike been prototyping some of their shoes or soles using this company's products. So it's quite interesting. So how has additive manufacturing really changed the landscape of manufacturing? If you think about it, in the traditional sense, you have a design process which involves drawing, modeling, optimization. You're not even sure yet if the part would work or function. Then you have to go prototype it, which costs a one-off manufacturing, which often is pretty expensive. During that process, you might see that there needs to be a new manufacturing process, or for example, how would you cut a certain geometry that is in your design, or you might even require a new type of material to be able to do the job that you want. So, for example, achieving a certain weight to strength ratio. And in the past, that's where most of the engineering happens. Then once all that has been done, you will go into the maybe possibly redesigning, optimization, and then mass production. which you employ companies like those ones in China with lathes and CNC mills and maybe casting. And that whole process is very lengthy and time consuming. One good thing though is that it employs a lot of people, but then that's a different discussion, I guess. So you look at this flowchart, you've got requirements, concept, prototyping, all funneling into the flow. But however, additive manufacturing generally just speeds this whole process through. You can get a design, prototype it, and because many of the techniques are developed already, you can actually print a range of materials that could suit the process. And because of the way you can create geometries that was not possible before, you often can get a very targeted type of physics in your parts. So if you look at how a bridge works, right, you will have trusses to distribute the load. You can actually create that whole system but using a porous network as a geometry base, which will show, additive manufacturing actually helps redesign parts in general. The problem though that you get from this new opportunity is uncertainty in a lot of things. For example, mechanical properties. Now, if you look at how the print are generally done, you can imagine how if you print the object vertically versus horizontally, you're going to get a very different profile. For example, this tensile specimen, if you print it like that on the X direction, your print is going to be in this form, in a way, in this form, right? But if you print it in a very different direction, you can actually get that configuration. And those two configurations will have very different strength profiles. So that's something to be cautious of. Print parameters, right? You may actually see some companies being able to produce parts that are cheaper, right? And that may be because they opt for less shells or different type of space filling parameter. So those things are often not talked about. And if you're actually an engineering firm producing, say, the next bracket for a GoPro camera holder, and then some other company comes up with the same idea, they could make it cheaper, but slightly less sturdy or less rigid. But no one's actually going to question too much about it. And so I think in general, people need to be educated that print parameters is very important for additive manufacturing, whereas design parameters were traditionally very important for the typical conventional manufacturing process. Just an interesting graph. You can see this bar graph shows a density percentage of different prints of titanium alloys for body implants. With the different types of print methods, you can see the density actually decreases. So the highest density is E-beams and kind of layer deposition. But with the laser sintering method, you actually don't get that type of density requirement. So that's something to be mindful of. Finishing is, as you can see, it's just the surface finishing. Issues with the type of layers, you can see the 3D printers are not all that smooth compared to some other method. You've got porosity issues and color palette basically. I'm sure you've seen on the news a lot about different types of materials being printed. We can even achieve glass, and in some weird cases you've got skin and biomaterials coming through, and medicine as well. So here's a very interesting research that someone has done in the US, which is printing materials that could fold upon being stimulated. So for example, you put this in a boiling water, it folds in a box. And you can imagine how you can use this as a way of capturing pollutions in a pond. You put it in the pond, and because of the pollutants in the pond, it actually captures it, and then you can use magnetization to kind of recapture the boxes and purify your water system. So there's been houses printed, anything that can be extruded can be printed. So chocolate, jelly, pizza, you've got pizzas is being printed often. You've got sugar cube, basically anything that can be deposited in some form and sintered together can be printed. Okay, so this was what I was talking about, a complete redesign of existing parts because of this availability to construct things that were not possible in the past. Now, this is a hinge. You can see conventionally you would take a block of metal and cut facets, remove parts. But because you're printing things from ground up, you can create organic designs such as this, which actually does the same job. And when you optimize them with the right loading, you can create structures like that, which has a third of the weight. So this system is a kilo. This is only 300 grams. Manifolds, right? Complete redesign of how a system would look. I'm just going to dive straight into the ethics behind additive manufacturing. Now, you can imagine how additive manufacturing allows everyone, all right, both rural type of people or city type of people, whatever, to have that manufacturing capability. This creates an issue because in the past, for example, guns and keys can only be manufactured somewhere. Now, if you have that capability to print things, you can replicate keys. For example, in the US, there was this incident where a lot of those generic skeleton keys were being printed and could just open luggages. You've got components of guns being printed and assembled, so anyone can actually make weapons now. So this opens up for regulation issues. Another thing is the environmental issue. There's been research showing that there are fine particles emissions from desktop 3D printers, which means everyone who has a printer in the little room, it's almost acting like a factory. So, in the past, you've got heavily regulated legislation on what a factory should be and what the ventilation standards are. With this 3D printing boom, you actually don't have those regulations in place yet. So that opens up a lot of boxes or a lot of doors that no one knows what's going to be behind them. And if you think about how much we're already generating, if you gave the manufacturing capability to everyone else, then you can potentially have even more waste generated. So, sustainability is an issue in the current world already. With this additive manufacturing process, although you're using less materials to create the parts, you're probably actually going to be creating more parts in that sense. So it's almost like when they first said email is going to replace papers, but in fact paper sales went up because everyone prints emails. So that's an interesting thought. Finally, despite all the negative effects of all this, you can see how additive manufacturing gives people the ability to create their own prosthetics, which in the past would cost a lot because it's been governed or only been able to manufacture it by global corporations. And giving this power in a way, or enabling technology back to the people, often open up and equalizes the community in that sense. So as a quick conclusion, you can see additive manufacturing streamlines the whole engineering manufacturing process. It opens up doors for creation of new material types as well as designs. Basically anything that can be extruded, sintered together or melt together can be printed. It's a very disruptive technology because it has legal and ethical effects that people may or may not have thought about. Creates redundancy and automation, which, as I said, with the employment issue could be an issue. Everyone has to now go into the design space rather than the manufacturing space. But at the end of the day, it's an empowering technology which could radicalize the world in many sense. Okay, thank you. would be Chuck Holt. So the old guy here. It's not that old, but this is the bloke who came up with this idea. But actually, I tried finding references to when 3D printing was first referenced in sci-fi. They can't actually find it because if you look back to Star Trek, it is an instantaneous development of the object. So that doesn't count as 3D printing, which is layered by layered. So I guess the only reference point is in the 80s. So Chuck was the first one to come up with the concept. Yes, but with the ethical issues. So in the US, there's already been companies printing stem cells and scaffolded tissues. But again, what differentiates a person from an object? That's an ethical realm that they have not actually solved. So if you use your stem cell and then start printing a part, put it back onto yourself, does that mean that part is actually yours? And if so, how many parts can you start replacing before you start becoming not you anymore? So there's an ethical issue that needs defining. Well, printing money has been a while, or it's been in for a while anyway. So counterfeiting is the general space there. But I don't think printing money is as much of an issue because you're only using money for transaction for something else. If you can actually get that something else yourself, then what is the use for money in that sense? Of course, maybe you can get better qualities of that thing using the money, but I don't think printing of money is what additive manufacturing would affect the most. Not too sure, to be very honest, because there is no such definition at the moment. But in terms of additive to those enhancements, it generally falls under genetics. In the past, places like some countries have training programs that have been breeding people in a way. It sounds a bit conspiracy-ish, but that is kind of what people do. They see that type of people have that gene to say play basketball really well, tall and all that. They will probably put a lot more resources in trying to get them to that arena. So, I'm not too sure what the guidelines will be, but it's not going to stop in any soon time. But yeah. I did see a YouTube of being able to print a child, but I'm sure it's not true. But if you think about it, yes, I think you can because you're simply printing cells, and that's what they've been doing, printing embryonic cells. You print it in a form that grows. If you grow enough parts of it, it becomes live. So in the very simplistic and generalized sense, yes, you can print, but it's probably not the same baby that you're thinking that just walks around and does things. You should buy a 3D printer that has some kind of exhaust to ventilation. So you can get cheap systems without that casing, but then you can also just manufacture your own casing with a little fan with pipe that goes out. Just because we're not sure what the negative side effects of the health issues relating to 3D printers in enclosed areas. So it's probably better to be cautious about it than to not care about it at all. Yes, so this is a very sci-fi question. I personally, I think you can, but then that falls into philosophy as to what defines a consciousness. If you start replicating someone with every single aspect of that person, do you then call that a replica, or do you call that the real thing, the real person? So You can definitely, technologically, you can probably do it, but ethically or philosophically, it's not really defined. Actually, they do that because once you can print the proteins, right, which is from DNA type of amino acid arrangement, you can print viruses. So the simple answer is yes. They actually have done that in China and in Amsterdam as well. So printing houses. This is a Disney castle printed in California, and this is one of the first 3D printed hotels in the world. And you can actually print bridges using systems like this that welds metals together. So yeah. "3D printing liquid will be pretty hard because you need to contain it. But if you have the confinement, then I guess why not? Often you use the liquid phase to create something solid with a certain geometry, desirable geometry. So often you polymerize liquid into solid.